Welcome to Fort Bend Tutoring. Today we will be teaching you on a new subject of which you might find interesting. Please put your cigarette down and pay attention for a minute.
Hello ladies and gentlemen, this is Mr. Witt with Fort Bend Tutoring, and today's tutorial is going to be about solving exponential equations. That's right. Okay, so let's check it out. So we have exponential equations, and you see before you the parent function of exponential equations. So all of our equations that we'll be solving today have a parent function of f of x equals to a to the x, where a is greater than 0 and a cannot equal to 1. So those are the conditions for the base in our equations right here. All right, so there's the form. All right, so let's get to solving some problems, shall we? All right. In problem number 1, we have 4 to the x equals to 2. Well, the first thing I'm noticing about this particular equation is that as a base, 4 and 2 have many things in common, but what I really want to look for is the smallest factor they have in common. In other words, the smallest base that they may have in common. And that means that I'm looking for the number 2. That's right, 2, because 2 to the second power is 4, and we already know that 2 to the first power is 2. I'm going to show that I could rewrite 4 as 2 squared raised to the x, and this equals to 2 to the first power, like so. Continuing on, anytime I have an exponent on the outside of a set of parentheses here, that exponent, when dealing with a monomial, multiply these exponents together. That's right. So I'm going to multiply the 2 and the x together, and I can go a step further and show that this will be 2 to the 2x equals to 2 to the first power. Oh yes. Okay. So now what I have is I have an equation with like bases on either side of the equal sign. When I have a situation like this, all right, that means that I can really just ignore these bases. The reason for that is because since my base is identical to one another, the exponents have to be equal as well. So being as though the equation read as 2 to the 2x equals to 2 to the first power, the 2x has to equal to 1. All right. So that's my preferred method for solving a problem like this. So my next step is to go ahead and show that 2x equals to 1 and then solve for x. Alright, so I'm dividing both sides by 2 here, and I find that x equals to 1/2. That's right, put it in a red box. Done. That's the answer. So let's recap, shall we? We started out with our equation, which was 4 to the x equals to 2. I recognized that I could get a similar base from the 4 and the 2, that being 2, and I rewrote the number 4 as 2 squared. Once I rewrote the equation, I then simplified it by multiplying the exponents together to end up with 2 to the 2x, which equals to 2 to the first power. Once I have a common base on either side of the equal sign, then I can go ahead and ignore the bases and set the exponents equal to one another and solve for our variable. So that's what happened. X equals to 1/2, red boxed. So let's move on to the next problem. In problem number 2, we have e to the 4x minus 1 equals to e squared raised to the x. So what I'm going to do here once again is recognize that I have a common base on either side of the equal sign, and what I want to do here on the right side, I want to simplify those exponents. Remember, anytime you have a monomial raised to an exponent, you'll multiply those exponents together. So I'm going to be bringing down this e to the 4x minus 1, which will now equal to e to the 2x. All right. So once again, we have the exact same base raised to an exponent. So the e's are canceled out. I'm going to be bringing down 4x minus 1, which equals to 2x. Yep, just like that. Then I'm going to solve for x. And you know what? I'm just going to subtract 4x to both sides here. I'm going to be bringing down that -1, which now equals to -2x. You got it. I will next divide both sides by -2. Oh, you already know what this answer is, don't you? So I'm going to end up with x equals to positive 1/2. Hey, another 1/2. Well, so be it. Let's red box it. Putting the red box around my answer. All right, so there it is. That's right. That's problem number 2. We are moving on now. Problem number 3. All right, in problem number 3, we have 3 to the x equals to 7. So unlike our previous 2 problems, notice that the bases, the 3 and the 7, they really don't have anything in common. No, they don't. So this is where you can start using your logarithmic rules, and I prefer the natural logarithmic rules, and for the simple manner that it's one less letter to write and I'm lazy. So I'm going to rewrite it as the natural log of 3 to the x equals to the natural log of 7. just like that. And using my natural log properties, I know that anytime I have this set up here, the exponent can come in front of the natural log as a coefficient. So I'm going to have this rewritten as x times the natural log of 3 equals to the natural log of 7, like so. Then, solving for x, that means I'll be dividing both sides by the natural log of 3. Okay, so once that cancels out, ladies and gentlemen, you'll now have x equals to the natural log of 7 divided by the natural log of 3. And that's your answer. That's it. Okay, now let's say that your teacher or text is requesting your answer to be written as a decimal to the thousandths place. Let's see what happens here, all right? So you want to input the question just as you had it written, as the natural log of 7 divided by the natural log of 3, and what you want to do from here is you want to press enter. All right, so this would be the result. All right, so as we're going to round our answer to the nearest thousandths place, your answer would be 1 and 771 thousandths. All right, so this equals to 1 and 771 thousandths, and that's rounding our answer to the nearest thousandths place, as some text and teachers would have you do. All right, so there you go. We're going to red box our answers here. So if they're looking for an exact answer, you can leave it as the natural log of 7 divided by the natural log of 3. Or if your text or teacher is requesting an approximation to the nearest thousandths place, this would be your answer right here. Okay, so for problem number 4, we have 2 to the 3 minus 2x equals to 8. So once again, I'm always looking at my basis and trying to find commonality. I'm trying to find the same base that could be used for every term inside of the equation. So what I recognize is that 2 and 8 definitely have a common base that I can use, and that number is 2. All right, so I'm going to rewrite this as 2 to the 3 minus 2x, and this would equal to 2 cubed, like so. So knowing that my bases are the same now, I can go ahead and kill these 2's here. All right, they're dead now. And I'll just bring down the 3 minus 2x equals to 3. From here, I can just solve for my variable x like so. I'll be subtracting 3 to both sides of the equal sign, bringing down negative 2x, which equals to 0, and then dividing both sides by negative 2. From here, we now know that x has to be 0 in order to make the original equation a true statement. And there you have it. Okay, just like that. X equals 0. Red boxing it. Just like so. Put those answers in a box. Let your teacher know that you're done. Don't have them searching all over the paper for the answer. Put that thing in the box, man. Put it in the box. All right, let's move on to the next problem. In problem number 5, we have the quantity of 5 halves raised to the x equals to 4/25. Once again, my first priority in order to make the process simpler for me is to try to find a common base that could be used. So the first thing I'm noticing is, okay, I got 5 halves working over here. It's raised to the x. So I'll just go ahead and bring that down as it is. But over here, on the right side, I'll show that 4/25 could be written as 2 squared over 5 squared. All right, well, this is close to what I want, but it's not exactly what I need, right? So let's keep working at it. Let's go ahead and bring down this 5 halves raised to the x. And next I'll be showing that if I were to shift the base of 5 to the numerator and the base of 2 to the denominator, I can rewrite it as 5 to the negative 2 power over 2 to the negative 2 power, like so. All right, being as though both of these bases have a common exponent of negative 2, that means that I can now rewrite this as 5 halves to the x equals to 5 halves raised to the negative 2 power. All right, so finally, ladies and gentlemen, I am showing that I have identical bases to the left and the right, which means the 5 halves can now be canceled. So I'll be bringing down x equals to negative 2, and this is my answer. I'm red boxing it. Red boxing. There you go. There you go. That's the answer, ladies and gentlemen. X equals to negative 2. That was problem number 5. Let's keep it moving. With our next example, we have example 6. We have 2 raised to the 6 minus 3x equals to 8 raised to the x plus 1. We're starting out with different bases, but I know that 2 and 8 have a common base of 2. So this is what's going to happen. I'll be bringing down 2 raised to the 6 minus 3x, and then I'll show that 8 can be rewritten as 2 to the third power, which is still raised to the x plus 1. All right, so that's going to be my first step. From here, I'll be simplifying on the right side by distributing that 3 to that exponent of x plus 1 here, all right, to show that it's going to be 2 to the 6 minus 3x, which now equals to 2 to the 3x plus 3. All right, so once again, I distributed the 3 to that exponent because, once again, anytime you have a monomial, one term, raised to a power, you can just multiply those exponents together. Oh, yes, you can. So now, what happens? Our bases are identical. What happens with that? Yep, you're right. They're going to cancel out. Goodbye. So I'm going to be bringing down that 6 minus 3x, which now equals to 3x plus 3. You don't like that 3 either? Okay, let me fix it. All right, that's a little better. That's a little better. Could be better, but we'll go with that. We'll go with that. All right, so now I'm going to solve for x. So that means I'll be adding 3x to both sides. Oh, yes, I will. And if you'll permit, I'm going to go ahead and subtract 3 to both sides as well. All right, so here we go. Our 3x's cancel out over there. On the right side, the 3's cancel out. I'll be bringing down positive 3 equals to 6x, and then dividing both sides by 6. If you got to be kidding me. We get another 1/2 here. We're getting another 1/2. All right. 1/2 is in charge today. So that's your answer. That's your answer there. X equals to 1/2. Let's go ahead and red box it. If I get one more 1/2, I'm going to do something dangerous. All right, so let's move on. Let's move on. Next problem. All right, in problem number 7, ladies and gentlemen, we have 2 to the x plus 3 equals to 5 to the 2x. Now, what you should do at the beginning of every problem is try to see if you can manipulate the bases to be identical. The 2 and the 5 don't have really anything I can work with here, which means that I'll be using my logarithmic properties, or my preference, the natural logarithmic properties. So I'll rewrite this as the natural log of 2 to the x plus 3 equals to the natural log of 5 to the 2x. From here, my exponents will become coefficients. So I'll show that the quantity of x plus 3 times the natural log of 2 is equivalent to 2x times the natural log of 5. You will then distribute on the left side of your equal sign here. And that means that I'll get my arrows popping here. So I'll be bringing down x times the natural log of 2 plus 3 times the natural log of 2, which equals to 2x times the natural log of 5. What you want to do now is you want to get all the terms that have your variable x on one side of the equal sign. So I'm going to subtract x times the natural log of 2 to both sides of my equal sign here. All right, just like so. All right, now I'll be bringing down 3 times the natural log of 2, which equals to 2x times the natural log of 5 minus x times the natural log of 2. All right, great. So once we have this form, the next thing that you want is to factor out the x. You're solving for x, ladies and gentlemen, so you want to isolate it. So that means that I'll be bringing down 3 times the natural log of 2, which equals to x times the quantity of 2 times the natural log of 5 minus the natural log of 2, like so. All right, so now we want to solve for x by dividing both sides by 2 times the natural log of 5 minus the natural log of 2, just like that. And yeah, I'm aware of that, ladies and gentlemen. That's right. You could go ahead and rewrite the 3 natural log 2 as natural log 8, and you could rewrite the 2 natural log 5 as the natural log of 25. You could do that. So it all depends on the form of the answer that you're looking for. Okay, so we'll take a look at that. Let's go ahead and show that x equals to, this 3 natural log 2 is the same as the natural log of 2 to the third power, which means it is the natural log of 8. All right, so you've convinced me. I'm gonna go ahead and write it that way. And then the 2 natural log of 5 is the same thing as the natural log of 25 minus the natural log of 2. If your text or teacher preferred exact answers, you would have the natural log of 8 divided by the natural log of 25 minus the natural log of 2. Or you can go ahead and calculate this with your calculator and round your answer to the nearest thousandths place. So I'll show you what that looks like. All right, so in your calculator it looks just like that. All right, and then pressing the equal button, we'll end up with our answer rounded to the nearest thousandths as 823 thousandths. 8 823 thousandths. And that's it. Let's red box our answers here. This is one form of the answer as an exact answer, and rounded to the nearest thousandths place, you have it written as 823 thousandths. Done. That's problem number 7. All right, let's move on. All right, in problem number 8, we have 27 raised to the 4x equals to 9 raised to the x plus 1. Well, what we want to do is we want to first of all see if we have a common base within our existing bases here. And normally it's a smaller number, ladies and gentlemen. So I see that 3 to the 3rd power is 27, and I also see that 3 squared is 9, which means I will be rewriting this equation like so. It'll end up being 3 to the 3rd power raised to the 4x, and this is going to also equal to 3 squared raised to the x plus 1, like so. Simplifying this further by multiplying these exponents, you'll have 3 to the 12x equals to 3 to the 2x plus 2, just like that. So because our bases are identical, I can cancel them out, and then I'll bring down 12x equals to 2x plus 2 and solve for x. And I'll do that by subtracting 2x to both sides of the equal sign here, and you'll have 10x equals to 2, and then divide both sides by 10. You'll have x equals to 1/5, just like that. All right, so 1/5 is the answer. Finally, another answer besides 1/2. All right, so this is our result, ladies and gentlemen. 1/5 in a nice red box. That was problem number 8. Let's move on. In problem number 9, we have e to the x squared equals to 100. Well, one thing I know about the constant e is that the value of it is approximately 2 in 718 thousandths, and its mortal enemy is the natural log. So that's what I'm going to use to solve this problem. I'll rewrite this as the natural log of e to the x squared equals to the natural log of 100. By taking the natural log of both sides of the equal sign, this allows me to cancel out that e. So I'm able to rewrite the equation as x squared equals to the natural log of 100. From here we'll implement the square root property. So that means I'll be taking the square root of both sides of the equal sign here, and on the right, just keep in mind that you'll have to have that plus or minus sign. And this is going to be the square root of the natural log of 100 on the right. Simplifying this, my square root and my square will cancel out, and x will equal to plus or minus the square root of the natural log of 100, and this is going to be one form of my answer here. So I could leave it just like this as an exact answer, or if I were to simplify this to the nearest thousandths, it would be equal to plus or minus 2 and 146 thousandths as a decimal representation of our answer here, rounded to the nearest thousandths place. All right, so it's red boxing it time. So our exact answer would be plus or minus the square root of the natural log of 100, and the other, it would be plus or minus 2 and 146 thousandths. Done. That was problem number 9, ladies and gentlemen. And now we're moving on to the next problem. In problem number 10, we have e to the 3x minus 7 times e to the negative 2x equals to 4e. Well, it's best to try to have one base equal to another base as far as solving these equations. So I'm noticing that I do have like bases on the left side of the equal sign, and that anytime I'm multiplying like bases, I can add the exponents together. So I'll be able to rewrite this as e combining 3x and a negative 2x will give me x minus 7, which will be equal to 4e. At this point, because e is a constant and not a variable, I can divide an e from each side of the equal sign. So what I'll show is that by dividing both sides by e, I can simplify this by rewriting this as e to the x minus 8. Remember that dividing like bases, you subtract the exponents, and this was e to the first power. So when I combined e to the x minus 7 minus 1, you end up with e to the x minus 8 here. On the right side of the equal sign, however, my e's will just cancel out and leave me with the number 4. So I'm going to take the natural log of both sides of the equal sign here, like so, and the natural log and the e will cancel out, and I can bring down x minus 8, which equals to the natural log of 4. Then, solving for x, I can add 8 to both sides of the equal sign. So as an exact answer, I can write it as x equals to 8 plus the natural log of 4. And that'll be my answer. If I were to calculate this and round my answer to the nearest thousandths place, my answer would be 9 and 386 thousandths. All right, so those are going to be your answers right there. Let's red box it. I have 8 plus the natural log of 4, or I can write it rounded to the nearest thousandths place as 9 and 386 thousandths. All right, and that does it for problem number 10. In problem number 11, we have the cube root of 5 raised to the negative x power, which is equal to 1/5 raised to the x plus 2. The first thing I notice in this equation is the number 5. Yeah, I have the number 5 underneath this cube root, and I also have the number 5 in this denominator here on the right side of the equal sign. So therefore, I'm going to try to see if I can rewrite the equation with a base of 5. So let's see what I can do here. Converting this radical into exponential notation, I can rewrite it as 5 to the 1/3 raised to the negative x power, which equals 5 to the negative first power raised to the x plus 2. From here, what I'll do is I'll go ahead and multiply the exponents together. Anytime you have a base raised to an exponent, then those exponents internally and externally will multiply together. So I'll end up rewriting this as 5 to the negative 1/3 x equals 5 to the negative x minus 2. And so here we are, ladies and gentlemen. That's right. Now that my bases are identical on either side of the equal sign, I can now ignore these, all right, and then just bring down that negative 1/3 x equals negative x minus 2. And since I don't care for these fractions, I'm going to go ahead and multiply everything by 3. I'll have 3 times negative 1/3 x equals 3 times negative x minus 2. I'll go ahead and multiply that out now. Simplifying this, I'll cancel out these 3's to end up with negative x equals negative 3x minus 6. All right, and that's the result because we distributed, in other words, got those arrows popping in that previous step there. I'm going to add 3x to both sides of the equal sign at this point, and I'll now have 2x equals to negative 6. Then dividing both sides of the equal sign by 2, we end up with x equals to negative 3. All right, so there's your answer. That's the solution. Red boxing it. You got it. Done and done. So that was problem number 11. Let's move on to the next problem. All right, and problem number 12, we have 3 times the quantity of 2 raised to the x minus 2 power plus 1 equals to 100. The first thing I want to do in problem number 12 is isolate the base that's raised to a power. So that means I'm going to start by subtracting 1 to both sides of this equal sign. So I'll have 3 times 2 raised to the x minus 2 equals to 99. There you go. Then I'm going to divide both sides of the equation by 3. So dividing both sides by 3 right here. And so now we have the base of 2 raised to x minus 2, which equals to 33. Done and done. So we have our base isolated. From this point, we can go ahead and use our natural logs or logarithm properties in order to solve for x. What I'll do, because I'm lazy, is use the natural log. Okay, so I'm going to have the natural log of 2 raised to the x minus 2 equals to the natural log of 33. At this point, my exponent can become my coefficient. So I'll rewrite this as the quantity of x minus 2 times the natural log of 2 equals the natural log of 33. All right, so we're going to distribute now. That's right, get our arrows popping. Okay, so I'm going to distribute that natural log of 2 to everything inside of the parentheses, and I'll rewrite this as x times the natural log of 2 minus 2 times the natural log of 2 equals the natural log of 33. Isolating the term with the variable x, I'm going to add 2 times the natural log of 2 to both sides of the equal sign. Just like this. And now I'll go ahead and bring down x times the natural log of 2 equals to the natural log of 33 plus 2 times the natural log of 2, like so. Let's go ahead and take this to the next page. All right, we want to solve for x, so that means I'm going to divide both sides of my equal sign by the natural log of 2. So on the left side of the equal sign, the natural log of 2 will cancel out. I bring down my variable x, and lo and behold, you really can't do much with the right side of the equal sign. So as an exact answer, the natural log of 33 plus, and then making that coefficient of 2 an exponent, you'll have the natural log of 2 squared, which gives you the natural log of 4 all over the natural log of 2. So you could submit this as an exact answer, or you could submit your answer in decimal notation rounded to the nearest thousands by using your calculator, and in that case you would have this setup here. So in decimal notation your result would be 7 and 44 thousandths. Notice how I'm showing you two different ways to input the problem into your calculator. In the first scenario, I used a simplified form of the natural log of 4 in the numerator. However, just to show you that the answer would be the same, you could also keep it in the form of 2 times the natural log of 2 in that numerator and get the same result of 7 and 44 thousandths rounded to the nearest thousandths place. All right, so there you have it. Alright, so this is the result as an exact answer, or you can have your decimal notation as 7 and 44 thousandths. Let's move on to the next one. In problem number 14, we have 2e to the 2x plus e to the x equals to 6. In a situation like this, we can use a quadratic process in order to solve it, especially if we're going to use substitution. I'll state that my y is equivalent to e to the x, and that y squared, therefore, would be e to the 2x. So let's go ahead and substitute these values in and then set our equation equal to 0. So I'll rewrite it as 2y squared plus y equals to 6. Then subtracting 6 to both sides of the equal sign, you'll now have 2y squared plus y minus 6 equals to 0. So I'll have y plus 4 times y minus 3 equals 0, dividing both the 4 and the 3 by 2. This now can be simplified into the following form. Y plus 2 times 2y minus 3, which equals 0. So this is the factored form, and now I'll use the zero factor property. Using the zero factor property, we have y plus 2 equal to 0. We also have 2y minus 3 equal to 0, and then you'll solve for y. So I'll begin by subtracting 2 to both sides so that y equals negative 2, and then adding 3 to both sides of my equal sign in the second equation. I'll have 2y equals to 3, then dividing both sides by 2, you'll have y equals 3 halves. Okay. So these are the solutions to y. However, we need to replace these values of y with e to the x. Remember, we use substitution. So going back to this first equation of y equals negative 2, we'll rewrite that as e to the x equals to negative 2. Then finding the natural log of both sides of the equal sign, we'll have the natural log of e to the x equals to the natural log of negative 2. And it'll show me that I have x equals the natural log of negative 2, which is impossible. It's undefined. So this is an extraneous solution. We can't use that. On the other equation, however, where we have y equals to 3 halves, we'll go ahead and show that we have e to the x equals to 3 halves. Then taking the natural log of both sides of the equal sign, we'll have the natural log of e to the x equals the natural log of 3 halves. So my natural log and the e will cancel out to give me a value of x that equals the natural log of 3 halves. Now, as far as the domain of the natural log is concerned, this is valid. You can have the natural log of a positive value, which is 3 halves, so that's okay. That means that this is the answer to our equation here, that even though our first possible solution was extraneous, the second one is a-okay. So this is going to be our answer for this problem here. And I'm boxing it up. There you go, ladies and gentlemen. The natural log of 3 halves, or writing your answer in decimal notation rounded to the nearest thousandths, you'll have 405 thousandths as a result. And there you have it. Done and done. All right, ladies and gentlemen, this concludes solving exponential equations from Mr. Witt and Fort Bend Tutoring. As always, please rate, comment, and subscribe. And if you're able, please donate, because that helps us bring you more free math videos from Fort Bend Tutoring. Peace.
We appreciate your time. Don't you want to learn mathematics the correct way? You need a foundation. Do not just be guessing at your numbers. Contact us today. Look us up on your Facebook at Fort Bend Tutoring. Learn it well, honey.